This section deals with a power series. And what we're looking at is a polynomial to equal a function. And if we look at an infinite polynomial, you can see that this is essentially just a Taylor series. And because each term is a power, we call this a power series centered at C. The domain of this function is the set of x's for which the series converges. Because this series only converges for certain values of x. For others it will diverge. Essentially what this says is that for some values of x, for some range of x, this series does a good job when it's centered at C of approximating f. For other values of x that are too far away from C, it's not going to do a good job. So for convergence of a power series, one of these things will be true. It will converge only at C, the place where it's centered, or there's a real number r that's greater than 0 such that it converges absolutely for the absolute value of x minus c less than r, and diverges for greater than r. Or the series can converge absolutely for all x. R is what we call the radius of convergence, and the set of x's for which there is convergence, the domain, is the interval of convergence. And to find R, we're going to use the ratio test. So here is our first example. We want to find the radius of convergence. To do this, we're going to do the ratio test. Remember, that's taking the n plus 1 term and if I plug in n plus 1 to the exponent, I end up with 2n plus 3. So we're dividing by the nth term, in other words, multiplying by its reciprocal. And because of the absolute value, the negative 1's to the power go away. And we can do some simplifying here. So x to the 2n plus 3 is the same thing as x to the 2n plus 1 times x squared. So I'm left with x squared on the top. And then 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, so those will cancel. Now this limit, as n goes to infinity, is equal to 0. So what this tells us is that for any fixed value of x, the series will converge. So the radius of convergence here is infinite. Second example, we're actually going to find the interval of convergence now. So first we have to find the radius of convergence. So ratio test we go. And what we're left with is negative 1 to the n plus 1, x plus 1 to the n plus 1 over 2 to the n plus 1 times the reciprocal of the nth term simplifying, we end up with the negative ones canceling, going away because of the absolute value. And then we have x plus 1 to the n times x plus 1. So we're left with an x plus 1 up there. On the bottom, 2n plus 1 is really 2 to the n times 2 to the first. The 2 to the n will cancel out, and this will converge, or this is equal to x plus 1 over 2, the absolute value of that. As n goes to infinity, that thing stays where it's at. And this will converge when that quantity is less than 1. In other words, when the absolute value of x plus 1 is less than 2. And what this tells us is that we are centered at x equals negative 1, x minus c, and the radius of convergence is equal to 2. And what we end up with is an interval negative 3 to 1, 2 units either side of where we're centered at, and not including those values. And what we need to do is we actually need to check those values. We have to check the endpoints. And if I plug in these numbers, let's see what happens. So I get negative 1 to the n, and then plugging in negative 3. For x, I have 2 to the n over 2 to the n. And this one's just going to go plus 1 minus 1 plus 1 minus 1. This diverges. And then plugging in x equals 1, take that back, plugging in negative 3, left with the sum of 1 to the n. Well, that diverges. So our interval of convergence is the open interval from negative 3 to 1. One of these endpoints might actually work. So we do need to check the convergence for those specific values of x. Now, if we have this series, this power series for a function, then on the interval of convergence, our function can be differentiated and integrated. These power terms are very easy to integrate and differentiate. We've used the power rule since the very beginning of calculus. So, we want to find the interval of convergence for this function, for its derivative, and for its antiderivative. So looking at the terms for this, we have x plus x squared over 2, x cubed over 3, and so on. Its derivative would be 1 plus x squared plus so on and so on. This can be written in summation notation as x to the n minus 1. The antiderivative of our function with respect to x would be x squared over 2 plus x cubed over 3 x cubed over 6 plus x to the 4th over 12, and so on. And that can be written as x to the n plus 1 over n times n plus 1. Of course, from n equals 1 to infinity for both of these cases. So now I want to check convergence for all of these. And I'll start with our original function. So applying the ratio test, and this is equal to the absolute value of x. So our function is centered at 0, and it has a radius of convergence being 1, and the interval that we get is -1 to 1 for its interval of convergence. And if we were to check the endpoints, we would find that plugging in x equals -1 does work. We get an alternating series that passes the alternating series test. But if we plug in n equals +1, it does not work. We get the harmonic series. So we have a closed interval at -1 to an open interval at +1. And now we're going to check these endpoints for the derivative and for the antiderivative. So for our derivative, plugging in both 1 and -1, we get 1 to some power, 1 to the n plus minus 1, and -1 to the n minus 1. Those both diverge. So this interval is an open interval on both ends. And then for the antiderivative, plugging in -1, we have to apply the alternating series test, and this ends up working. It ends up converging for x equals -1. What we end up with is -1 to the n plus 1 over n times n plus 1. I should go back and correct that typo. This series goes from n equals 1 to infinity. So applying the alternating series test, the limit as n goes to infinity of 1 over n times n plus 1, that does equal 0. And a sub n plus 1, which would be 1 over n plus 1 times n plus 2, that is less than 1 over n times n plus 1 for all n. So this is decreasing. So by the alternating series test, -1 does give us a convergent series. It satisfies both those conditions of the alternating series test. Now when we plug in +1, we end up with 1 over n squared plus n, and we can compare this to a convergent p-series 1 over n squared. And for this, 1 over n squared plus n is always less than 1 over n squared for all n. So by direct comparison, x equals +1 also gives us a convergent series. So we get a closed interval, -1 to 1, for the antiderivative being convergent. Here are the problems to work on for this section.